Okay, let's begin. This is going to be my last lecture. I am looking forward to it so I can follow Vishwanath's lecture without having to worry about preparing for these lectures. We are going to talk about the Kac-Weil character formula. And a few basic facts about the Weil group of an affine algebra of an, I will do only the untwisted case. These are the agenda items for today, but we are some distance from reaching that goal. So what I will do today is give you the basic definitions. I'll try to put down the correct statements. I will skip many proofs, but I will also hope to do many different kinds of simple calculations which will hopefully give you an idea of what is going on and maybe help you go to Katz's book and make an attempt at reading it. Okay. I will have to skip proofs, there is no choice, but I do nevertheless hope to do some key calculations. Okay. So let's talk about integrable representations. So let GA be a Kac-Moody algebra. Now, could somebody tell me what this means now? So what do we understand by that statement now? What is GA? GA is the algebra constructed in the fashion that was described by Punita. That is, you take the relations, the obvious set of relations except the Serre relations, and then go modulo the ideal that is maximal with respect to not intersecting H, right? That is GA in general, but what does it, that we, if you, the way it is done in Katz's book, and Punita was also following that, I guess it is a standard notation, that is not in general called a Kac-Moody algebra. What you call a Kac-Moody algebra is when you start, when that matrix A is a generalized Cartan matrix. Yeah, it's when the matrix A is a generalized. When it is symmetrizable, you call it a symmetrizable Kac-Moody algebra. Okay, it could be, the algebra could be symmetrizable without being Kac-Moody. I suppose when the matrix A is symmetrizable, you call it GA symmetrizable algebra. So this means that this A is a GCM. Yesterday when we talked about the invariant form, the standard form, invariant form, or the normalized invariant form, the GCM property didn't really come into the picture. It was the symmetrizability of the matrix which was important. You will see here for this definition of integrable, which somehow has to do with the notion of integers. So let me give you an idea of what this might mean. So these modules which will have some kind of integral weights that take, so you know what that means, right? Where the weights are take integral values on the co-roots. And another point that you should keep in mind is how do you prove any such integrability condition? you just restrict to an appropriate SL2 and quote. That's it. And the same thing works here. And the proofs aren't any difficult at all. Once you see what to do, you just look at it that way, and from SL2 theory the proofs fall out. What is an integrable representation? It is V is a G module V is integrable if the EI and FI, if all the EI and Fi act locally nilpotently. So, what does locally nilpotently mean? Given a V, there is a power of, and given a I between 1 and n, say the size of this matrix is 1 through n, these are the so called Chevalier generators. So, there is a power of E that kills the V, there is a power of F that kills that power could change with V, it could increase with V. So, this is the definition, and here is the main example of an integrable representation, the example adjoint representation. Here you will see that this is required. The fact, I will do a certain calculation, I will not prove this, but I will do a calculation now which will use the axioms of a generalized Cartan matrix. Okay. So, what is the calculation? So, as I said, I will not prove this, but I will do a part of it which is quite interesting, namely what I am going to show you is, so take Fi, which is one of the elements in the adjoint representation. I take another Fj. If it is going to act locally nilpotently, there must be some power of the Fj which kills this, and I am going to claim, okay, I will choose this to be J, add Fi to the minus Aij plus 1 equal to 0. That is interesting in two ways. One, it checks a particular case which uses the conditions here, and so illustrates how the conditions are important. The other thing is that it's the Serre relation. So, it tells you that the Serre relation holds. Okay. So, it has that double purpose. So, let us just do it. This is a very pleasant calculation. So, let us just do this. So, this is how so let us look at, so how am I going to show that some power of it kills it? So, I am going to show that there is this ideal we have gone modulo, which is maximal with respect to not intersecting H. So, you look at this element in G tilde A, if you wish, and then show that the ideal it generates does not intersect H. That will do the job. Then it must be 0 in GA. So let us, how do you do that? Well, you check sort of that it is the highest weight vector, in the sense that if I act the EIs on it, it will get killed. It's a weight vector clearly. Okay, so the proof goes by proof enough to show. So here is enough to show that the EI kill or EK kill Why is that enough? Okay. So what is the module generated by this? I act UG on this. Now, when I act the E case, it gets getting killed. When I act the H's, it's obviously a weight vector. And so the H's will act as scalars, and the remainings will be only F's. And those will come on the on this side. So you see that it gives you an ideal which does not intersect H. That's roughly the idea. But anyway, this is an interesting calculation. Let's just do this. So let us take first E. So EK commutes with Fi and Fj for I not equal, k not equal to I and k not equal to j. Let me write it correctly. If I not equal to k and I not equal to j. Correct? So if I apply E k there for such a k which is not equal to I, not equal to j. Okay, so there is Katz writes it this way, so I am writing it this way. But you can actually just write this. If you think of this as an element of the module, you can just write this where the action is add, right? So what does it mean Ek commutes? It just means it goes through. So when add, so it comes here, Ek on Fj is 0. So it goes through this and then it kills this. So that's easy. So let us take Ej, or should I take Ei? Let me take Ei. Okay. In this case, what is Ei of Fj? Ei, I not equal to j. So this is I not equal to j. Let's do this calculation, Ei, I not equal to j. Ei on Fj is 0. So right, and this is a weight vector. Now you apply SL2 theory. Ei on so Hi on Fj is A Ji, yeah. Is that correct? So by applying that SL2 3, what do I get? Ei on, so this is like I have to keep writing my favorite way of writing it. This again appeared in Ravindra's lecture in a different notation. This keeps occurring again and again. Is lambda minus n plus 1 y to the n minus 1 v. If xv equal to 0 and hv equals lambda v. That's the condition. Okay. So let's do that. So can you tell me please what is, so this is like add fi to the I, what do I get? Ei fi to the minus aij plus 1 fj is equal to lambda, which is minus aji and minus n is this. So minus aij plus 1 plus 1 of fi on times fj. Okay. So what do I get? Aha, okay. No, this is not, okay. I should have, okay. So, sorry, this will not help me. So I should write a slightly, let me write a slight variant of this, that will help me. So if you work with this, I'll get the following, sorry about this. This I think again, maybe Sandamarai wrote this down. There is a version of this which will give you this. Okay. Now let's apply that, and then what do I see? So so I want to compute EI on Fi minus Aij plus 1 and then Fj. So I write the commuting thing and then write push the EI here, correct? This I can write as EI Fi minus Aij plus 1 commutator Fj plus Fi minus Aij plus 1 Ei Fj, right? But this is 0. And what is this? This is Fi minus Aij. So if you want, let's do this with divided powers. So minus Aij into H. H is Hi minus Aij plus 1 acting on Fj. But Hi acting on Fj is A minus Aji. So what do I get? So Aji plus Aij plus 1 minus 1. So this is what I get. Okay. Now if one of them is 0, so there is still more work to be done. So if what are the properties of the Cartan matrix? If one of them is 0, the other is 0. So if Aij equal to 0, then okay. Okay. If Aij is not equal to 0, well, I should have gotten the right one. Did I? Did I write the correct
I think it should be
AJI? Okay, what is my notation? So this is my vector, this is my I. Alpha j acting on alpha I check, right? So that is ij, that is okay. That seems all right, but here. Thank you. So here it is it ij? It's a alpha j acting on hi, which is alpha h. Good, thank you. You saved my day. So this is then it's 0. Okay. Okay. So I wanted to do the other calculation also, but having got stuck on this, I'll skip those. But this is how it goes. So we've used the fact that it was an integer was used there, and the nice thing will be when so EI we have checked, EK we have checked. Let's do, okay, you talked me into doing it. Let's try EI, EJ, okay. EJ, that's an interesting calculation. So EJ, J is not equal to I. Okay. Now what happens? The EJ goes through this. And what does Ej times Fj give me? Hj. Okay. Now Hj, okay. So notice that Ej of Fi to the minus Aij plus 1 times Fj is equal to, it goes through this, Fi minus Aij plus 1. EJFJ acting in is Hj, right? Now notice Fi acting on Hj gives me some multiple of Fi. So if this is the moment this, and then if it acts once more, it kills it. So is equal to 0 if minus Aij plus 1 is bigger than or equal to 2. That is minus, which means what? Aij is less than or equal to minus 1. Okay. Now, what if the only question is when Aij is 0? That is the interesting case. So, we have done this except in the case when Aij is 0, in which case you use Aij equal to Aj. If Aij is 0, then Aji is 0 will come in. So let's do that. So assume Aij is equal to 0, then what are we calculating? Then we are calculating Ej on Fi Fj. This is what we are calculating. So let's do that. That is Ej Fi Fj plus Fi Ej Fj is Hj what is Ej on Fi? So let me get the correct coefficient. That's 0. And this is Aj is the other one. So this is also 0. So because Aij is equal to Aj equal to 0. So see, we've used all the conditions. Okay. So this is the principal example of a integrable module, and there are many lemmas in CARTS which say that how to check whether a module is integrable. For example, if on generators of the module the EIs and the FIs act as locally nilpotently, then the module is integrable. Okay. It's enough to check it on generators, the condition. But we'll skip all that. Those are formally very easy to understand once you understand the definition and some key point. I thought this was the most interesting calculation in that in that proof. Okay, here is I'll just begin to write down a proposition. I won't even completely write down the proposition, but I'll let you sort of see how it, extrapolate it in your minds. Here is the proposition, and CARTS says this is the reason why this proposition explains the reason why for the terminology integrable. V integrable and then you let GI, this is how CARTS writes it. So this is an SL2 copy of SL2 sitting inside your GA in your CARTS MODI. So V decomposes. This is the key point of integrability. V decomposes as GI module into a direct sum, possibly infinitely many, of finite dimensional, irreducible, H diagonalizable submodules. So when you look at it as this particular, when you restrict it to this particular SL2, it will decompose into finite dimensional sum of finite dimensional irreducible modules which are H diagonalizable. Not just HI, exactly. And what this means is, this means already that the weights must be integral. This is true for every I. So it takes every weight takes integer values on every coroot, and it also means that all this Ravindra was doing this morning, if something is a weight, then you can the SL2 string through it must be continuous, and if this has a certain weight, then the certain other weight must have at least that much dimension. All this will follow by applying the SL2 theory with which we are familiar. So I will not worry about writing down the entire detail of that. So I will write here .. C CARTS 3.6. So use this SL2 theory. the finite dimensional SL representation theory of SL2. Okay, now let me come to start defining the while group. So that was one of the topics for today. So what was the while group in the finite case? You had this root system, and I mean, in the finite dimensional case, we defined it for an arbitrary root system, and then the root space decomposition gave us a root system, and we said that the while group was the while group of the root system. Here too, I suppose you could argue that something on similar lines, but we will define the while group directly as acting on H star. So I will always be between 1 and n. N is the size of this matrix A, and I am taking a Kac-Moody algebra. G is a Kac-Moody algebra. Which means A is a GCM. That is, A is n cross n GCM. So I am going to define the so-called simple reflections on H star, and then claim that my while group is the subgroup of the general linear group on H star generated by these elements. That is going to be my definition. So let us define SI, and it is defined just like in the finite dimensional case. So SI of V is defined to be V minus V. So V is an element of H star. Alpha I check is an element of H by fiat, and so I write alpha here. Okay, now alpha, thank you. So this is a pseudo reflection So why do I call that a pseudo reflection? See, normally when you say reflection, you are assuming that you have an inner product space and you are reflecting along the orthogonal reflection along a hyperplane. Here it's called a pseudo reflection because it leaves a hyperplane fixed and it sends one element to its negative. Okay, so it has eigenvalues 1, 1, 1, 1, 1 and the minus 1. That's it. So this is a pseudo reflection obviously, because if alpha I check is a non-zero element of, because the alpha 1 check through alpha n check were linearly independent elements of H by fiat. Therefore, this will leave a hyperplane, this will kill a hyperplane in H star. So for all those V's, this is going to be, SI is going to fix it. And what does it do to alpha I? I get alpha I minus alpha I check, alpha I. But what is this? This I read from the Cartan matrix, which is AII, but it's a GCM. One of the hypotheses is that it's 2. So I get alpha I minus 2 alpha I, which gives me minus alpha I. Okay, here is where the 2 is used. And the definition of the while group is that, yes?
Pseudo reflection has another meaning also.
Okay.
Defined dimensional K.
Okay.
1, 1, 1 And the last character need not be minus 1, any omega.
Ah, okay. So maybe,
Therefore, we end it.
okay. So this is definitely a pseudo reflection, but the definition I gave of pseudo reflection is probably not general enough. Okay. Yeah. Thanks.
This is in fact a reflection.
Oh, this is what is called. Should I remove the pseudo?
No, what I mean is I think Vishwanath called it a reflection.
Oh, this is a reflection? Okay, good. So that's even better. So I will remove the quotes also. So quotes are back. Huh.
May not be minus 1.
Yeah, it can be anything. Okay.
Any finite or anything.
Okay. Okay. So be that as it may, this has whatever the correct terminology is, 1, 1, 1, 1, 1, minus 1. Okay. And this is defined as a subgroup here. In fact, let's also observe the following. Now, if A is symmetrizable, see what did you know about the Weil group in the finite case? It was in the it's an orthogonal group. I mean, it sits inside, it's above the orthogonal group, which means it preserves the killing form. So what should it naturally do here? It should preserve the invariant form, provided the invariant form exists. So you assume, so the observation is, assume A is symmetrizable, in which case the invariant form exists, and then check in that case that the Weil group indeed preserves that form. If A is symmetrizable, then W preserves the invariant form. The standard invariant form. So I will, this is an easy calculation. I would have liked to do it. It's also very pleasant, but for want of time, I'll skip that. But I hope at least it is natural enough to expect, right? This is the analog of the killing form, and you would expect the Weil group to preserve it, and it does. And it's an very easy checking. Okay, and let's make a couple more statements. There is also in Katz's book the relation between the Weil group of the dual Kac-Moody algebra, which you construct by taking the transpose of A. Okay, you can take the transpose of A and construct, and you will get a dual Kac-Moody algebra, and it will have a dual, the Weil group of that will be dual to this in the correct sense, but we'll pass over that and go on to the following proposition, which says, again a key fact, if V is an integrable module over a Kac-Moody algebra, then the multiplicity of a weight space, I forgot an important element in the definition of the integrable module. It should be H diagonalizable. Please add that. Otherwise, I cannot make the statement that I am making now. So it should be H diagonalizable. That's part of the definition of integrability. Okay. So I can talk about this, right, because it is then it's a natural thing to expect. Okay, and again it is proved using, how would you prove such a thing? Well, the while group is generated by these SIs, and this SI is, to check this on this SI, you just do it at the SL2 level. And so the proposition that I didn't write down, that will tell you, that would have one of the items saying that if you look there and look here, those two are the same. The dimensions of those two weight spaces are the same. And you would use that to prove this statement. So in particular, because it says roots are the weights of the adjoint representation. So just the special case of this tells me that the root system is W invariant. Moreover, and by this, multiplicity of alpha is equal to multiplicity of W alpha for alpha in a root and W in the while group. And there is a lemma which is very easy to prove, and I will not do it, and whose finite dimensional analog you have seen and used several times. So I just record this, and it says if alpha is in delta plus, that's it's a positive root, and SI, in our notation SI is always a simple reflection of alpha is negative, then what can you say about alpha? Alpha I. It is there is only one positive root made negative by alpha I, namely alpha itself. Okay? That's easy to see because if you write it as a sum of simple roots and apply S alpha to it, and you can, I will not say anything more, it's very easy to do. So W is generated by involutions. Pardon me? How do you? No, it is given to us because the roots, every root is either, when you write it as a linear combination of the simple roots, all the coefficients are either positive or, non-negative or non-positive. That is, from the very construction of the algebra you get it. And so I call them positive and negative. So many of these things like simple roots, like positive roots, negative roots, etc., and every root is positive or negative, comes by construction. Rather than you starting with a general algebra and then proving those things. Here it is sort of given to you by.
It's like that alpha 1 excess alpha is declared as base.
Yes, it is declared as base, yeah. And you observe that every root must be a linear combination of these, and moreover, that it's either all the coefficients are non-negative or all the coefficients are non-positive. That's an observation you make. So W is generated by involution. So you can talk about length of an element a reduced expression, etc. So if you have an element, if you have a group and it is generated by order 2 elements, a set of them, then it is easy to make this, the shortest way you can write it as a product of these is called the length. The reduced expression would be any expression which attains that shortest length and so on. Like in the finite dimensional case, I don't know if this term was mentioned, Coxeter group. This W is a Coxeter group. I will say what it means in this particular case. So W is a Coxeter group. What that means is the following. So this is no more, no less than the following statement. It is generated by S1 Sn by definition. So suppose I take these to be free generators and put the conditions Si square equals 1. Each one of these is an order 2 element because it's a reflection, and so it's order 2. Involution, I just meant order 2 element. That's all I meant. Yeah. So if you
That's okay. It's a standard.
and the following thing holds. So Mij is, you take Mij to be the order of Sij in W. Okay. See, W is generated by these. This relation holds in W. So does this by the definition of Mij. So what am I saying? It looks like I'm saying nothing. What I am saying, in fact, is that see, all it means is that this generators and this relations maps on to W. The content is saying that it is actually isomorphic to W. That's the meaning of this statement. So that's what it means to be a Coxeter group, and you prove this by proving what is called the exchange condition. Okay, so this is an important thing in the theory, but for lack of time we are unable to say anything more. So you establish the exchange condition and show that W's, that will tell you by, and there is a reference to Bourbaki which will tell you that this W must be a Coxeter group. Anyway, the statement at least is clear enough. This is all this means. Okay, the proof, however, is non-trivial. Okay. Now there is one more thing I want to say about the Weil group, and that is important for So here is a description of the Weil group. So this is what I'm in the untwisted case. So let us look at, I want to make a statement again. I won't be proving the theorem that I will state, but I hope to do once again a key calculation. So this is, if you want to look it up in Katz, this is 6.5. So what is H in this case? So now we go to the particular description. Okay. We are not working anymore with the abstract thing, but we go to the concrete realization of the affine. So we have alpha naught, alpha. Now I'll use L, because L is the n is the size of the matrix A. This was the extended Cartan matrix of a finite dimensional Cartan matrix, which I assume to be L cross L. Okay. So these are the now n is equal to L plus 1, and this is the extra co-root that I've added. And if you remember, this was minus theta check plus k. So where, if you remember, G A was G dot, that's the underlying simple, tensor with this Laurent polynomial ring, and then add a k and add a d as a vector space, of course, and there was this part was the universal central extension of this loop algebra, and then d was the degree derivation, and you form the semi-direct product. This is how it was done. So H, so these are living in H, and what is H for us in this case? This is H, the underlying, you identify G naught with the tensor 1. So you can think of H naught as sitting inside this GA plus CK plus CD. Okay, now let's observe. So here is the observation. Observe. So let me also recall for you the roots. So there is alpha naught, alpha 1, alpha L. So these are the, you can think of them as roots in the original underlying finite dimensional space. So this would be contained in H naught star, which I think of being contained in H star by sending k and d to 0. See, if you have a subspace, the dual of the subspace is naturally not sitting inside the dual of the bigger space. It's the other way around. There is only a map from the dual of the bigger space to the dual of the smaller space. That's the natural map. But here we want a map this way, so you have to choose a splitting, and this is we have a splitting. So with respect to that splitting, I define this. Okay. And recall that alpha naught is minus theta plus delta, where delta and k lambda naught, where see delta and lambda naught are dual to k comma d, d and k respectively. So delta is an element of H star. It is 0 here, it is 0 here, and 1 on D. Lambda naught is 0 here, 0 here, and 1 on K. That's the definition. Okay. Now let's observe that W of delta is equal to delta for all W in W. Why is that? So there is this element delta which is fixed by all, it's fixed by the entire while group. While group acts on H star, delta is an element in H star, so it makes sense for me to talk about W. How do I compute W of delta? To do this, it's enough to check that on each of the simple reflections. So I try apply one. I take delta minus delta alpha I check alpha I. But if it is one of these, then delta is 0 on that, 0 on H naught. Delta is 0 on H naught. Therefore, these live in H naught. That's done. And if it is this, there is only a K component. There is no D. So that's easy to see. And I define the underlying as okay. You might say this is bad notation because this should represent actually the underlying while group of the finite group of the finite dimensional algebra, but actually I'll define it in a different way and then show that it is actually the notation is justified. So this by definition is the subgroup generated by S1 through Sn. And observe that delta of alpha I check is equal to for all I between 1 and n. Between 1 and n, not 0 and n. So what that means is that on the space Ck plus, sorry, where am I? So the while group is acting on H star. H star I should look at delta and lambda naught. So the delta and lambda naught are vectors. You can imagine them as perpendicular vectors in H star. And you can look at the two-dimensional plane spanned by those. That is fixed by this subgroup. Because it does not, none of this moves delta or K. Also, H naught star is W naught invariant. What we are driving towards is that this W naught is actually the group of is a finite while group. Okay. Now that again is obvious because how are you going to change it? Take an element of H naught star. If you apply one of the SIs from here, 1 through L, how are you going to change it? You are going to add an element of, some multiple of that coroot, but that coroot lives in H naught star. So what I get is that W naught to GLH naught star is faithful, and I can identify, and maybe this takes just a little bit of observation, but I will just say it, and we may identify W naught with W of G naught, thus justifying the notation. So in particular, this is finite. This is nothing but the underlying okay, now let me try to give you the description of the while group, the bigger while group, in terms of this is one part of it, and there is another part, and I will describe that while group as a semi-direct product of this while group and a translation group, which I will just say how it comes about. So I'll try to explain this. If you try to read cards here, it is a pretty technical and difficult in terms of notation. But so I have to try to understand it in a slightly simplified way. So I'll try to explain that. So think of this. So I will draw, this is a picture of my H star. I am trying to draw a picture of H star. So I'll put H naught star on one axis. I'll put delta on this axis. I'll put lambda naught on this axis. Okay. Now look at the plane where the coefficient of lambda naught is 1. Okay. I claim that plane is fixed by W. So this plane is fixed by W, not pointwise, but invariant, W invariant. Okay. Instead of writing something, let's think through why this should be true. What do I do when I act by a W element? I have, so SI of V is V minus something times the coroot. Now what are the coroots? You add something in H naught star, or you add plus K. Right? Sorry, I should say this, no? I should say this, yeah, minus theta plus delta. This is what I add. Okay. So you're never going to change this. So if you start with something 1 lambda naught plus something something, you're going to take that minus something times one of the alpha i's. But the alpha i's will involve only something in H naught star, or change the delta part. It will not, it will fix the lambda naught part. So that's the simple observation that it is left W invariant. Okay. Now I'm going to say one more thing, that there is a, this is just my way of understanding it. Maybe there are, you would prefer a slightly different way of expressing the same thing. So there is a C action. Let us take a C, the group C, the additive group C action on this plane. Let's give this a name, this P. Let me call this P. On P, by you send lambda there. So if I take C, which is a element of the complex number, I said lambda to lambda plus C delta. Okay, now let's observe, here is the claim. Now the W action commutes with the C action. Okay. Now let us observe again. Let's say this is, it's better than writing anything down. Let's just go through this. I claim the W action commutes with the C action. That is, if you take a lambda here, move it by a delta, act W, it's the same thing as first acting W and then moving by delta. So what should I show? Adding the delta will not change the inner product with any of the alpha I checks. That's what I have to show. But what are the alpha I checks? They are these, and there is a K only. There is no delta in it. So it's obvious that this is the case. Yeah. So what happens? So you have one action and another action, and they commute. So you can, the action of W goes down to the space of orbits. And what is the space of orbits here? All the deltas are, you can push it to 0. So I can just get, you can think of the space of orbits as H naught star. So Thus, the action of W goes down to P mod the action of C, which is which you can think of as H naught star. Okay. Now, again, you can observe that the finite while group acts on this as if it was the original action. Okay. So, the only question is how this extra element S alpha naught acts. Okay. And for that, let us we make an observation. So, S alpha naught S theta of lambda, if you, okay, this was again a very good calculation to have done, but for want of time, since I want to start talking about the Kurzweil character formula, I will not do this, but it's a very good exercise for you to try, because you know how the theta checks, you know all the information, that everything is explicit. So, I am going to write down something and ask you to check that. Okay. And what it says lambda, so lambda is in H star. If you do this computation, you will get lambda theta. Theta is the longest root. That's our in all this, when we defined this, you recall theta was the longest root, or no, highest root. And one more thing that you will probably need to use, or at least you will be happy to use, will come in handy, is that the normalization is that theta is 2. You fix the form such that theta is 2. Okay, there is a form which comes into the central extension, the way this Lie, the Lie algebra thing on the central extension is defined, the Lie algebra multiplication. So, theta is the, so that theta is the highest root, plus, so mod delta. Okay, so let's see this, what it means. If I take lambda is in P, so this is the statement. This is the statement I want you to check. And if you do this computation, and now you put lambda is in P, if lambda is in P, then what do I get? I get S alpha naught S theta of lambda is equal to lambda plus theta. Because the P has elements of P have lambda naught coefficient, meaning it comes with 1 lambda naught. So, that with K will give me 1. So, it is lambda plus theta mod C delta. So, if I look at this action here, interpret this action here, this is nothing but translation by theta. So, thus, S alpha S theta naught, S alpha naught S theta acts on it moves it by theta. So, see what is our while group? It is generated by S alpha 1, S alpha L and S alpha naught. S theta will belong to, S theta is something in the finite while group. So, it will be some product of the S alpha i's for I between 1 and L. Okay. So, I could replace the generator S alpha naught by S alpha naught S theta. It will not change it. So, what do I expect the while group to be? The while group should act on this by translations by theta and its while group translates, and the original action of the while group itself, the finite while group itself. So, this I hope gives you an idea of the following statement, which whose proof I will not do, but I hope with this it should be convincing enough that while group is isomorphic to the finite while group, semi-direct product, the long root lattice. By which I mean the lattice of long roots. That is, the lattice generated by the long roots, because theta is a long root, okay, and all its while group translates will be long roots. So, this is the statement. Okay, now, in the remaining time I will talk about the Katz's while character formula. So, let me write down, it looks very much like the finite dimensional situation. So, if except that the denominator is slightly different. So, GA be symmetrizable Katz model. So, my A is symmetrizable as well as generalized Cartan matrix. Yeah. So, lambda dominant integral weight. So, what does that mean? It is an element of H star. It takes non-negative integral values on co-roots. That is what it means. Then okay, L lambda, I will go back and forth between, let me choose lambda here. L lambda, let me say the corresponding irreducible representation. Okay. Now, that requires some comment. Okay. What do I mean by the corresponding irreducible representation? Now, in the finite dimensional situation, you saw that there was a 1-1 correspondence between elements of H star and Verma modules and their irreducible quotients. Okay. So, there was a 1-to-1 correspondence between irreducible modules with the highest weight vectors, and I'll ask Vishwanath to be careful here and check if what I'm saying is correct. There's a 1-to-1 correspondence with irreducible modules with highest weight vectors and elements of H star. That's a correct statement, right? So, you take the corresponding Verma module and take its irreducible quotient. There is no other way it can be. If it has a highest weight vector, it has to be a quotient of the and is irreducible, it has to be a quotient of that Verma module, and there is no other way. Okay? And if it has a so here too, so I didn't talk, I had some idea to talk about it, but that's I'm not so unhappy about skipping it, because all that part about Verma modules, maximal vectors, primitive vectors, etc., works exactly the same as in the finite dimensional case. And like I was saying yesterday, the proofs are not even analogous, they are literally the same. So there is a corresponding irreducible representation, which is the quotient of that Verma model. Okay? And we are talking about the character of that. And so the statement is character of L lambda is the summation over W. I'll write sine of W, or minus 1 to the length of W, or epsilon of W. No, not epsilon sub W, but maybe some other, okay, any one of those. Exponential of W dot lambda, or I'll be more explicit and write this. So instead, the denominator is slightly different. So this is the formula. So the top is just as in the finite dimensional case. The denominator is written differently. It's a product instead of a sum. There you would have written sine W exponential of W of W dot rho. That's what it is. W rho minus rho. That's what you would have written.
Here is not half sum of
Yes. I will just come to that. Yeah.
It's not unique also.
It's not unique. Yes, exactly. So so the question you should ask yourself, what is rho? What is rho? Okay. Now rho, you cannot define it as half sum of the positive roots. Okay. So, but in Sandam Ray's exercise set, he had another description of rho, namely prove that it is the sum of the fundamental weights. Now you could try to use that, and what does fundamental weight mean? It is a fundamental weight is one that is dual to the coroots. Okay. Now the coroots don't span H star. Coroots don't span H. They are only a part of H. So what you do is rho is any element of H star such that rho on alpha I check is 1 for all I between 1 and n. Now I am back to the notation where A is an n cross n generalized Cartan matrix, symmetrizable generalized Cartan. Okay, that's correct. So this is the definition of rho. Okay. Now let us try to do as much as we can about the proof of this. So let us try to understand the denominator a little bit. Okay, so the rest of the lecture will be about some ideas of the proof of this.
In the finite dimensional case, there is a one-one correspondence between dominant integral weights and finite dimensional irreducible representations. And here,
Irreducible representations.
so here you would have integrable.
Correct. You would have integrable. Yeah, exactly. Integrable. Maybe you should say integrable category O representations. Let's see. What would be the I would say integrable category O representations. So let me see if I can make that statement. I have it written down somewhere here. So let me, since you mentioned it, it's an important theorem, so let me Let me put it down. Okay. It says a GA module B in O is integrable if and only if it is a so this is the notation for dominant integral weights. Okay, so indeed these are the irreducible elements in O int. Okay, good. So this is the statement of, if you want, of complete reducibility. So if you take so if I take an element, this way statement, if I take an element in O, category O, which is integrable, then it's a direct sum of these irreducible modules, which are also integrable. And the proof of that is uses the Casimir in much the same way that we did in the finite dimensional case. And I will recall for you, and you should do that exercise if you haven't done so. I outlined in an exercise the how to do it for SL2, and the proof in Katz and is very similar to that. It's just jazzed up version. The ideas are all appear in the SL2 case itself. Okay. Now let's. Thanks for reminding me to state this. So now let's look at that. So we have this, I will write out a few obvious identities. So if I have that, then it is 1 plus so I can write so let me call this R. So this is notation, and this Katz uses this too. So let's put this let's call this R, and then I can say, observe that 1 minus R, 1 over R is equal to in the notation of that Sendamare was using, P lambda, the small p lambda, E lambda. I'll use exponential and E interchangeably. So this was the constant partition function. That's one observation. And the other important observation is that so you can write down the character of the Verma module. So character of, if m lambda is my Verma module, this is Verma module with highest weight lambda. How can you write it down? It is just a free module over un minus, right? So you can write this very condensed way as that. That's an important observation. Okay. So now let me talk through the steps of the proof of this Kurzweil formula. So here is one proposition. Let V be in category O. Although, so V, you cannot say that V has a composition series. See, our definition does not admit a composition series would mean even allowing infinitely many terms such that the quotients are irreducible. Even that it does not admit, but although V does not admit composition series, and this is the technical part of the proof. What you can do is, we can nevertheless talk about how many times an irreducible module occurs in V. Okay, there is some way of defining this multiplicity, and character of V will be equal to character of V L lambda. Sorry, this times character of L lambda. Now let's do okay, never mind this. This is probably the least interesting. Let's go on to a slightly more interesting calculation. Okay, so here is. So I'll make a bunch of statements. What does category O mean for us? So it had those that the weights were all there were finitely many things in which the weights were all down below. So observe that category O modules are restricted. What does restricted mean? It means that given any element, only finitely many of the positive roots act as non-zero. So if you have a category O module, you have an element state, you can assume without laws of generality to be a weight vector, it will be somewhere. How many positive roots can act? The answer is it commutes with all elements of G or UG. Therefore, it preserves weight vectors. So that weight vector, the highest weight, and that is single dimensional. So it will have to send that V to a multiple of itself. So that V will be an eigenvector. Okay, and then by the same argument we'll show you that it acts as a scalar. Okay, so then, and this Casimir we have seen lives, once it acts, it is in the U of the center of the universal enveloping algebra. Yeah, or rather, not that way. It commutes with all the actions of the G. That's a better way of saying it. So then this acts as a scalar. And what is the scalar that it acts as? So calculation, and this is perhaps one of the most important calculations in the book. It says this is the scalar that it acts as. Okay? So do you want to, here is a very quick, let's very, do I have permission to go a little over? Okay, so I want to do this calculation, and in fact I want to say a few things about the, few more things about the proof which are important, I think. So, and I hope I'm not tiring you. I hope you've following what I'm saying. So let's do this. Okay, so what is, let's recall what this is. If you recall, this was 2 nu inverse rho plus what was that, sigma ui, right, plus 2, then there was a alpha bigger than 0, then there was an s, and then there was an e minus alpha s, e alpha s. That's what it was defined as. Okay. Now, it acts as a scalar, so I choose the highest weight vector and act it on it to compute that scalar. I can choose any vector, I choose the highest weight vector. So what happens to this? So I only have to compute this. Okay. So let's compute it. And this is again a very pleasant computation, but I will so how does this act on V? So what does this nu inverse rho mean? It is the element rho represents in H when you pull back. Okay. So 2 rho acting on V is twice nu inverse of rho acting on lambda of, right. But what does this mean? This is the definition of nu inverse of V. So this acts as 2 lambda rho. Okay. Now, what does this act as? Okay, these are, what is this? This represents all the elements of, this is a dual basis for H, I mean, with respect to the form. Now, that's again a very pleasant calculation. So here is a homework. Show sigma ui acts as, see, roughly it should act as lambda square. I mean, it's sort of at least believable if I say this, and it's a calculation. Okay. Now, so what do we have? Lambda lambda plus 2 rho v lambda. Plus 2 rho lambda. Now, by a simple calculation, that is just this. Okay. Now, even in the finite dimensional case, this is very interesting calculation. But it works also just as well in the infinite dimensional case. Okay. Now, a few more statements. So, here is an important step in the proof. So, let me write Ch of V. So, if V is a highest weight lambda, then this is equal to, I will write it like this. I think Sennabare was using this yesterday too. I will give you an idea of why this must be correct. C mu in Z, C lambda equals 1. Why is this true? Well, you have a highest weight vector with lambda. So what does that mean? It is a quotient of the Verma module. So in trying to compute its character, I can compute it as a Verma modulo quotient something, and then keep trying it step by step. And if I try to do that, what do I see? I see first of all the character of the Verma module corresponding to lambda, and then plus minus the rest, the other high, the others which are sitting inside the Verma module, a sub of the Verma module. Okay. Now, if you take a sub of the Verma module, you can again take some other Verma module mapping onto that sub. Okay. Now, but that is the highest weight vector. So, if you have one Verma module sitting inside another, they are both highest weight vectors, highest weight modules, and the Casimir will act by the if it acts by the same scalar, which tells me that this thing must be the same on both of them. That's what gives me this condition. Okay. So, this modulo some induction will give you, as Chandamare was doing last time. Okay, just one more pleasant thing, and I will stop with that. Okay, so now we apply, try to apply this. So I know by this that if now I apply this to my, take V to be my L lambda, very good. I take V to be my L lambda. What do I see by doing that? I can write character of L lambda is equal to some C mu. So let me isolate maybe the first, well, never mind. C mu, CH, M mu. But this is something, the reason for writing this is that you know what this is. This is that E mu by E mu by R. Okay. Now, so you are reduced to showing R times E minus rho CH L lambda is equal to, let me see if I, E rho is equal to C mu E rho plus mu. So I have this. So then now I am reduced to calculating what these are. That's all I have to do. Okay? And here is a very, again, it's a very pleasant exercise. Check that this is W skew invariant. What does that mean? When I act an element of W on it, it varies, it transforms as the sign of W, minus to the sign of sub, yeah, minus of the length of, yeah. It's a very pleasant exercise. Okay. And therefore, you will see that this must also transform. See, okay, now I'll just skip to the last line of the proof. This must also have that property, but these form a basis, which means what about this? These must be, and I know that rho plus lambda comes with coefficient 1. Okay? So I see that anything else must be a Weil group orbit of that rho plus lambda, and further the coefficient there must be the sign of that W, which is the formula. Okay? So it's a very hand waving proof, but that's what it is. So thanks a lot. Thank you.